Okay, so what I want to discuss today is the setting of collective states. And now, since I am very, very bad with times, I'm putting time limit over myself. In networked phase oscillators, I'm very glad that a lot of things about synchronization was already presented by Jürgen in the previous talk. And I'm going to describe some phenomena like explosive synchronization and some new states that you can find in connections to such a phenomena like the Bellerophon states. These results were obtained by a large group of collaborators you see over here, which are part of this international research team we are creating on networks and data science, which is called the Stefano Nadir, and you see here the logo. So synchronization is a very old problem in physics. And actually, it was discussed by Christian Huygens in the 17th century, so you see. And he discovered that two pendula which are hanging to the same clocks are giving rise to a collective motion, which he called sympathy, not synchronization. The fact that the two pendula sets their oscillation in antiphase, and he was able to understand very well that the reason for the setting of such a collective state were the tiny forces where the two clocks interchanged, the tiny coupling, because they were hanging at the same wooden beam. And they were suspended at the same wooden beam, and so they were interacting among them. So he really understood that interaction between oscillatory elements can give rise to setting of collective motions. Now, in modern era, we refer to models which are not pendula, but oscillations. And let me spend 2-3 minutes to describe you a very paradigmatic model, which is the Kuramoto oscillator. So in Kuramoto oscillatory system, you have an ensemble of many oscillatory elements. Each of these elements is characterized by a phase, this phase theta, and in absence of any interactions, it has a natural frequency omega n. It means that each of these elements can be represented as a point in the unit circle, which is rotating or counter-rotating depending on the sign of this natural frequency omega. And so what you do, you take a lot of these elements, a big number of these elements. You imagine that frequencies of these elements are different. That is, each oscillator has its own natural frequency, and they are randomly taken from a usually known frequency distribution G omega. So you have a distribution of frequency, and all the frequencies of your oscillators are different. And then, when you have such a large ensemble, you couple them, and the coupling that you consider is simply the sum over all the elements of the sinus of the phase difference. So each element n is calculating the phase difference between his phase and the phases of the other elements, summing up and multiplying by d, which is the coupling strength. So now I'm moving to this movie. So I'm showing a movie, and you see what happens when you take 1,000 of such oscillators and you slightly increase d. Okay, so let's start the movie again. Sorry if I get it back. So initially, the oscillators are distributed on the unit circle with no apparent correlation between their motion. And when you increase the coupling strength, you will see that this a bunch of oscillators will group, will coalesce, will collapse into a single cluster, you see very well, which then, once it is formed, starts to move with the same frequency and the same phase around the unit circle. So basically, they synchronize. This is the classic Kuramoto model. And I want to describe now a small variance of this model, which is what happens when we consider networks. And we want to describe in this talk, basically, what happens in the transition between the fully incoherent state, which is this, to the fully coherent state, which is the clustered one. Okay? So we will try to describe this transition. In order to describe this transition, we need to monitor what is happening in our system, and a way to monitor this is to refer to the Kuramoto order parameter, which is nothing but taking the unit vectors associated to each one of the oscillators, summing up, and then taking the modulus and divided by the number of oscillators. So if the oscillators are all coherent, you are summing up, this vector coherently, and so you obtain that this sum has modulus almost n, and when you divide by n, you get 1. Whereas when the oscillators are in the incoherent states, they are distributed along the unit circle, you will have a counter oscillator, a counter phase. So the two vectors are actually almost annihilating. And when you make the sum of all these vectors, you get something which is similar to 0. So what we want to describe in the Kuramoto model, actually not exactly in this one, but in the Kuramoto model with networks, the situation in which you pass from incoherence, the distribution of the oscillators are practically homogeneous in the unit circle, to the fully coherent, you have a unique cluster solution, which is called the synchronized solution, by means of some intermediate state. And the key point is discussing what happens in these intermediate states. I repeat that we are using a slight modification of the Kuramoto model, in the sense that since we want to describe this in networks, we have to take into account that the different oscillators are not interacting all to all, but they are interacting on a structured network. And therefore, what you have to do, if you have to take the classical Kuramoto model and just to plug here the adjacency matrix of the network. So now this matrix is a matrix of zeros and ones, and all elements equal to 1 denote the presence of a link between the node n and the node m. Oh, now you see immediately which are the two ingredients of the cake. The two ingredients of the cake are the frequencies, the initial frequencies that each oscillator has, the natural frequency. So in our case, the frequency distribution that you assign, and the topology of the connections, the way these oscillators are interacting in the network. And now we are going to see that depending on these two ingredients, you can cook, you can make a cake such that you can control, if you want, the transition between the two states in a way which is important, and in a way in which you can pass from some kind of phenomena to some other kind of phenomena. In particular, when in physics you are dealing with phase transitions, which means that a given system changes between two states. In our case, it's incoherence and synchronization. But in physics, you have many other examples of a system that is making a transition from one state to another. Then you have basically two kinds of possibilities. You have a control parameter. In our case, the control parameter is nothing but the coupling strength, how much, in our case, is what we defined a few minutes ago, that is the order parameter by Kuramoto, the R parameter. And you can have either a transition which is continuous, smooth, and reversible, which is typically called a second order phase transition. And this implies the fact that if you prepare the system in this state, in state 1, and you gradually increase the control parameter, you will have a transition to state 2, by means of a continuous smooth curve, and reversible. Reversible means that if you do the opposite, that is, you prepare the system in phase 2 here, and you gradually decrease the control parameter, you actually are making the same transition exactly in the same curve. So it's a purely reversible system. That's one possibility. The other possibility instead is to have a discontinuous transition. That is, your system stays in state 1 for a given while, up to when it jumps in a discontinuous way to state 2. And moreover, this is typically sometimes, not always, but sometimes is typically associated with non-reversibility. That is, if you now prepare the system in phase 2, in state 2, and you gradually reduce the control parameter, you jump down to state 1, but you jump at a different value of the control parameter. So you define a region between these two, which is the forward transition, and this is the backward transition, that is typically called hysteresis. So I don't want now to end up with the story because I have no time. I want to go back to this, and I want to tell you the main message of the issue. The main message of the issue is this. What is happening in between pure incoherent and pure coherent states? The typical case of Kuramoto model, for example, it's a smooth transition, second order like. And the reason is that here you see these oscillators are all around the unit circle, but here, when you arrive here, you have the formation of small, very small cluster of oscillator. Imagine that you have two oscillators which by chance have a very close by initial frequency. So they first synchronize and they form one small cluster here and another small cluster there, and many, many others. So you have the nucleation here of small cluster of synchronization. This cluster, when you increase further the coupling strength, can do two things. They can grow in the sense they can attract to themselves other free-running oscillators. So a cluster with 2 attracts another oscillator, so it becomes cluster with 3. And then it grows again, and merge. So you have two clusters of two distinct frequencies that they merge together, they collapse together, and form a larger cluster of a unique frequency. So imagine what happens here is a continuous process of growing, merging, growing, merging, growing, merging, up to the point in which only one cluster exists in the system, which is having all the oscillators in. So you have reached the synchronization solution. So if you want, so this is the typical case of a reversible second order like transition, which happens in many, many oscillators. And for so long time, since the beginning of the Kuramoto oscillator, it was thought as the way the system has transitioned to synchronization. If you want instead to observe irreversible and discontinuous transition, that this phenomenon that was called explosive synchronization, because suddenly your system from a given state passes discontinuously to synchronization, what you have to do is to introduce some mechanism which prevent, some frustration mechanism, which prevent this cluster from growing, or which prevent these clusters from merging. So if you have this frustration mechanism, the system cannot make this continuous transition and is somehow forced to stay in a given state because you are preventing to do so, up to the point in which it has to jump altogether to the synchronized solution. So basically, what you have in this case is a situation in which your system stays frozen in a given solution, and then suddenly an infinitesimal produces a finite, big, large, and discontinuous jump in the order parameter. we want to describe the situation. And I repeat, I have no time here to discuss about story. It was this transition thought for the first time at the beginning of the last decade. I want to, and also, you see, if you want to see experimentally, we started reproducing this transition experimentally. So we started with a very small network of circuits, of electronic circuits, in which each circuit had a different frequency. But then when you couple them together, according to how you make the frequency, you can have a transition to synchronization. You see, this is the Kuramoto parameter. It goes from almost 0 to almost 1 in a continuous way, or in a discontinuous way, like the blue and like the red curves that you see in this plot. So the issue is, how can you make a general proof that first order like transition, that is explosive synchronization, that is this jump, can occur generically in a network of Kuramoto? And the first step we did is, let's now demonstrate first that if you give me, remember that we have two ingredients of the cake. One is the degree distribution, one is the network. So let's now fix one of the two ingredients. So let's fix the degree distribution, the frequency distribution. And let us demonstrate that once you have a frequency, when you fix the frequency distribution, you can always construct a network which make the synchronization transition explosive. So in order to do this, what you do is basically you take your ensemble, these are your oscillators, you see, and you fix the frequencies, because you distribute the frequencies according to the frequency distribution G omega that you have given. So this is, you cannot touch the frequencies. And now we want to say, we want to show that once you do this, immediately you can construct at least one network, at least one, which make the system synchronize explosively. And in order to do this, what you do is you pick now randomly a pair, EJ, for example, this oscillator and this oscillator. And now you check the frequency difference. And only if the frequency difference is larger than a given threshold gamma, then you put the link. Otherwise, you don't put the link and you choose another pair. So you start putting links, and you continue up to when your network has a given connectivity. This, you already reach the level of average degree that you prefixed. Now, what happens in your network? In your network, you have a network, but you never have direct connections between two elements of very close by frequencies. Because in order to put the link, you explicitly made the condition that the frequency difference you see, omega I minus omega j, should be larger than a given value. Then you use this, you continue, you take the network defines for you an adjacency matrix, and you study this equation, which is the Kuramoto model, in this kind of network. And what you find is that if your gamma is 0, so you don't put any constraint, basically you pick any pair of points and you always put the link, you obtain an Erdős-Rényi networks, a random network, and the transition to synchronization, this S is nothing but R, is continuous. You see, for gamma equal to 0, you have a continuous black line. Then if you increase gradually gamma, what you have is that the transition becomes steeper and steeper up to the point in which for gamma equals 0.4, you get explosive synchronization. So now the system gets frozen in the incoherent state, jumps for this value of D to the coherent state, the synchronous state. And when you do the opposite, you start from the synchronization state, and you see that you have another jump, but sorry, you have another jump, but you have this jump at a different value of D. So you have an explosive synchronization with hysteresis. And this is moreover interesting because you can calculate rigorously the distribution of the generated degree in the network as a function of the original frequencies. Because, you know, since you have put a threshold gamma, if you are this node, you cannot form connections here and here, because you can only form connections with nodes whose frequency is more than gamma from your frequency. So with these nodes and these nodes. And then when you take this 2 gamma segment and you move from 0 to 1, you can calculate exactly which is the expected function that should relate the final degree of your nodes with the initial omega I, the initial frequencies of your oscillator. And you see that in connection with the emergence of explosive synchronization, you have the emergence of correlation. You know, this is a very well correlated structure, is a V-shaped structure. And this happens, for example, when you fix initially Gaussian distribution, but you have the same V-shaped structure for any other distribution. This, for example, is an asymmetric distribution that you fix initially. So basically, this demonstrates that once you give me one ingredient, the frequency distribution, I can give you the other, the network. But we want to do something much better. Okay, so this means that you can generalize this constraint to many other situations. Now we want to do something even better. That is, now we want you to give me both ingredients. That is, I want you to give me the frequency distribution, but also the network. So I am not able to change the network. So I'm in the situation with the nodes on the table, each node having the frequency because you already fixed the frequency distribution. And also you fixed the network structure, this AIJ. So the only thing I can do is to wait, to give some weight to the existing links. I cannot add new links, I cannot remove links. What I can do, I can add weights to the existing links. And I want to demonstrate now that you can always find one distribution of weights such that for any initial frequency distribution and any initial network, your system is synchronizing explosively. So what you do something very similar. So you put a weight to the node, to the link ij, which is proportional, you see, to the frequency difference to a given power alpha. So the more if alpha is positive, this means that the more the two oscillators have a close by frequency, okay, the smaller is the value of the weight. On the opposite, for positive alpha, if two oscillators have very, very large frequency mismatch, they have a very large weight. It's very similar idea of putting a threshold. That is, you promote the links between far away oscillators in frequencies, and you shrink the weight of the links between those oscillators which are potentially synchronizing very easily. So you are putting a frustration mechanism, you see, in the synchronization. If you do like this, you see that when alpha is equal to 0, so basically you are not waiting, because alpha equal to 0, this term is always 1. You obtain a second order transition. Smooth, continuous, reversible, everything. When alpha is equal to 1, you obtain something very nice. You obtain a sort of universal transition, which is independent on the frequency distribution. So you see, I here report the curves for different frequency distribution One is uniform, Gaussian, bimodal, Rayleigh, semi-Gaussian, and at alpha equal to 1, these curves overlap perfectly, which means that independently on the specific frequency distribution, you have always the same explosive transition. And moreover, you have again the emergence of a V-shape property of correlation, this time not between the degree of the node and the frequency, but between the strength, or what Jürgen called intensity of the node in his presentation, and the weight. And you can also control the width of such hysteresis by further weighting with another important structural quantity in a network, which is the betweenness, the edge betweenness. And if you take into consideration a second weight in edge betweenness, you can, you can show that you can shrink or enlarge this hysteresis, so you can shrink or enlarge the irreversible region of the transition. Okay, so I am more or less left with 15 minutes, and so I have no time to discuss. There are many other ways you can put frustration mechanism in the system. We discussed, for example, situations in which you don't need to have emergence of correlations, but nevertheless, I want to discuss, to use the next 15 minutes to describe this important new state that emerge in connection with the change in the synchronization transition properties. I think I have convinced you that the transition to synchronization can be first order like or second order like. So let's now prepare a system in which I can have both possibilities. So I want to consider a system in which, depending on the parameter, I can be first order like or second order like. This is possible by slightly, again, modifying the Kuramoto model and introducing heterogeneity in the coupling with the mean field. So the idea is you have now all oscillator coupled with the mean field, and the coupling, instead of being a constant, independent, equal for all oscillators, has a value Ki. And this value Ki is nothing but K, a constant, the coupling strength, times the original frequencies of the oscillators. This means that all oscillators are coupled to the mean field, because you see there is now no network structure, but they are differently coupling in the sense the fast oscillators have a larger coupling strength to the mean field, and the slow oscillators have the lower coupling strength with the mean field. And moreover, we take frequency, because from a particular bimodal Lorentzian distribution, which is here described, so a distribution with two peaks, one in plus omega 0 and the other in minus omega 0, with delta. And then you have that depending on omega 0 divided by delta, that is, depending on the ratio between the location of the peak and the width of the peak, this g omega can be unimodal or bimodal. And then when you change this ratio, actually you change omega 0, you see that the transition can be first order like or second order like here at the end. So for what we learned before, in this case, when you are second order like, you have a region, an intermediate region, which is made of clusters that grows and merge. Whereas when you are in the first order like here, transition, you don't have cluster in the middle. You are frozen here up to when you have to jump, so no cluster. And so the issue is, what is happening in between? So if we now concentrate in the critical point in which this transition passed from first order to second order, that is here, you see, or here, what happens in the middle? Should I observe clusters or shouldn't I? Because if I am first order, I shouldn't observe clusters. If I am second order, I should observe clusters. So what happens in the middle is that I observe a new state, which is called the Bellerophon state. And I want now to describe it for you. First of all, the system is solvable. So we solved it rigorously. And so you can find the exact value of the critical points for both transitions, for the forward and the backward transitions. And you obtain the backward transition is independent on our parameter omega 0 divided by delta. This is the rigorous line, and then the dots are the numerical experiments. And therefore, you can calculate exactly the value at which you have the passage from the first to the second order transition, which correspond to a value, sorry, what is? To this point, okay? So you can put yourself exactly, I'm now lost okay. You can put yourself exactly in omega 0 divided by delta equals square root of 3. When you put yourself there, you start then increasing the coupling strength because you want to see what happens in the completely homogeneous case, and in the middle. And now look at these plots in which I'm reporting the instantaneous phases, the instantaneous frequencies, and the long time average frequencies of the oscillators for different values of the coupling strength. So when coupling strength is very low, I am in a fully incoherent state. So you see that there is no correlation in the instantaneous frequencies, no correlation, apparent correlation in the phases, and no correlation also in the long time average of the phase. On the opposite, when the coupling strength is very large here, and you obtain that all the phases are locked, all the frequencies are locked, all the time average frequencies are locked. When you are in the middle, you see 128, 160, 180, 2.10. In the middle, you have the formation of a state which is quantized in the term of long time average of the instantaneous frequencies. So you see, this plateau are all multiple of a fundamental frequency. But if you look at the states, at the oscillators forming this cluster, this plateau, these are oscillators which show exactly the same long time average of the frequencies. They don't show the same phase, and they don't show the same frequencies, instantaneous frequencies. So you are forming cluster of oscillators which are not phase locked, which are not frequency locked, are only mode locked, in the sense that their time average of the frequency is locked. This means that the instantaneous frequency, look at here, of each oscillator is a time periodic function, is a time periodic function. And very importantly, this time periodic function is organized with a particular rhythm, which is then reflected by the different value of the plateau of the long time average of these instantaneous frequencies. This is a lot of words. Let me show you what you have in a movie, okay? So what you have is a non-stationary, from the point of view of phases, non-stationary system in which the instantaneous phases, frequencies, instead of being locked to a constant in time, are periodic. And what you have is therefore a situation like this. I take now all the oscillator forming cluster 1 here, all the oscillator forming cluster 2 here, all the oscillator forming cluster 3 here, all the oscillators forming cluster 4 here. And you will see this oscillator that jump from one side to the other side of the unit circle periodically in time. So you see this movie, and you see that, for example, look at this oscillator. They distribute, they go here, but they don't stay here forever. I've come to the other place. And they will do this forever in a periodic way. And moreover, what is interesting is that the period for which cluster 1 is doing 1 jump, cluster 2 is doing 3 jumps. Cluster 3 is doing 5 jumps. So that's why you have an odd multiple of a fundamental frequency. Okay? The fundamental frequency is this frequency, the frequencies of this double jump, this periodic oscillation, this periodic motion. And here you have 3 times the frequency, 5 times the frequencies, 7 times the frequencies, which therefore produce for you very nice and very important and very, I would say, interesting novel behavior in terms of the global rhythm of the cluster. If I now take cluster 1, and now I rename this cluster 1, 3, 5, because there are multiple frequencies. So you see, if I take the oscillator belonging to cluster 1, and I'm calculating only on these oscillators my Kuramoto order parameter. Remember, Kuramoto order parameter in general is a complex number. In the complex plane, imaginary part, real part, I have a motion which is period 1. It's periodic, period 1. At the same time, if I now take the oscillators forming cluster 3, I have another periodic motion, but it's period 3. And if I take the oscillator forming cluster 5, I have period 5, and so on and so forth, period 7, period 9, and so on and so forth. So these states, these new states, which I repeat, they occur in between pure coherence and pure incoherence when the transition is exactly at the bifurcation point from being explosive, corresponds to asymptotic non-stationary rhythmic state. And for each cluster, the order parameter depicts complicated periodic patterns in the complex plane. Now you can tell this is, however, occurring in a very specific system in which you prepare the system very well to have a 3 critical point, because we are one transition point and another transition point. So you are in a 3 critical point. But in fact, you can prove that this is very, very general. For example, we can extend the validity and find Bellerophon state in case in which, instead of having this strange situation, you have 2 populations of oscillators. One population which is coupled positively with the mean field, which are called the conformists, and one population which is negatively coupled with the mean field, which is called the contrarians. So imagine that you have n oscillators, you have a fraction of them which is conformist, and a fraction of them which is contrarians. So the oscillator with positive k will behave like conformist in the sense they will attempt to follow the global rhythm of the system, and those with negative k will react as contrarians in the sense they will oppose to the main bit of the mean field. So when the system is only composed by contrarians, when you only have contrarians, it was shown by Strogatz and collaborators that the dynamics is fully incoherent. But then you can take now a fraction of these contrarians and flip to conformist. And depending on the fraction, on the number of conformists you have, at a given number, you can see synchronization. So if the proportion of conformists exceeds a certain threshold, then the system undergoes a transition to the coherent state. Now, in order to flip this, you can do in different ways. And you know, again, that's very important. The system is again fully solvable. So for this specific case, so for each one of the case, you can give the rigorous solution, you can find all the transition thresholds and so on and so forth. So you can make this flipping from contrarians to conformists in 3 different ways. The first way is randomly. So you decide, you choose randomly, independently on the frequency, I mean, on the original frequency of the oscillators. You take randomly some oscillators and you flip. Or you continue, you want to flip, so to say, imagine the 5%, then you take the first 5% in the frequency distribution. So you start from the one with higher frequency. Then the second, you take the one with a little bit less frequency. And so you follow the frequency distribution and you take the first 5%. Or you can do the opposite, that is, you can take the last, you can start from those with lower frequencies and going back. So you have 3 different ways of doing this. And for each way, you can take the 2 values, the positive and negative, can be equal in absolute value, or one larger than the other, or the other larger than the one. So you have a 3 times 3 matrix of possibilities of transitions, and you see that indeed Bellerophon states occur very, very frequently in all such possible configurations. And these states are very much the same as the one I described before. Because if I show you now, again, the famous plot of instantaneous phases, instantaneous frequencies, and time average frequency, you see that you have the passage from no synchronization to full synchronization by means of this staircase situation. You will see much better here. You have a large cluster of oscillators which form cluster 1, a smaller cluster of oscillators which form cluster 3, then cluster 5, 7, and so on and so forth. And again, in each one of this cluster, you have this V-shaped value of the instantaneous frequency, which means that the instantaneous frequencies are time periodic, and they are doing exactly what I was showing you in the movie. Then you can have also mixed case, that is, you can take heterogeneity in the coupling and couple them with conformist and contrarian. So you have this case, and then you have a very, very rich situation where Bellerophon states can occur, and also hybrid states, which are the superposition of odd Bellerophon state and even Bellerophon states, occur with very, very strange and always periodic, but not very nice like it was before, much more complicated structure of oscillations in the complex plane, referring to these hybrid Bellerophon states. Okay, so I am left with 2 minutes. And I want to leave you with the list of some material that you can find interesting to read. On synchronization, there is an old but nice tutorial that we wrote together with Jürgen time ago. And there is a recent book I published with Sasha Pisarczyk 2 years ago for Cambridge University Press. Then if you want to read something synchronization in networks, there are 2 physics reports which are quite popular, one dealing with complex networks, structure and dynamics, and the other one dealing with multi-layer networks, so networks of networks like the one that Jürgen just presented. Explosive synchronization in networks, starting from the first observation of Diego Passot on 2005 up to the recent papers, and we already published here another large monography where you find discussion almost on every aspect of explosive synchronization. And the Bellerophon states are studied in these papers, which are from 2016 to one paper last year. Thank you for your patience. And I have to make an announcement. Please submit your best papers to chaos oscillators and fractals. It's a journal of our community, which is growing very much in this year, and is now reaching visibility, very, very nice visibility. Sasha Kramov is one of the editors of this journal. Misha Ivanchenko is one associate editor of the journal, and is now converted into the top and most prestigious venues in the world for statistical and nonlinear physics. And the important point is, be aware that since this year we made an internal rule, which we are very proud of. And this internal rule is that we accept only 5 papers per authors. So we don't want to receive, I mean, if you want, we want to do something. We are the only journal in the world which are making this rule. We want really that each author use our venue for his best 5 journals, and at the same time we want to avoid, you know, some bad situations that there are of many papers published in a journal by the same author. One reason for which our journal in the past had problems and now is completely revitalized. So thank you a lot. I now finished my presentation. I'm open for any kind of question and discussion.